On this one, we will be solving question 8. And as you can see here, question 8 here, this is technical sciences. So we have that a potential difference of 120 volts is applied across two parallel plates of a capacitor, right? So the plates are 6 millimeters apart and have a 2 meters squared area, right? So that is the area of the capacitor, that is the area of the plate. Yes, and then this plate, they are the two parallel plates of the capacitor, right? So a force of a potential difference is being applied there, right? So now the first question here is asking you just to define in 8.1 there. We just have to define what is capacitance, right? So 8.1, that question, it says we must define what is capacitance. So according to our exam guideline, the capacitance, it is just the amount. So okay, let me write capacitance. Capacitance is the amount of charge. So capacitance is the amount of charge a capacitor can store. So remember what a capacitor is. It's a device that can store charge, right? So capacitance, this one is the amount of charge now a capacitor can store, right? The amount of charge a capacitor can store per volt. Yes, and then now that is the definition for capacitance. So 8.2.1, calculate the capacitance of this or of the capacitor, right? So when we have to calculate the capacitance of this capacitor, we can see that this capacitor now, we have the applied the potential difference, which is the voltage, the V, which is 120 volts, and then we also have the distance, right? So when they say this capacitor, if we can draw this capacitor, so we have one plate here, and then we have another plate there of a capacitor, we have another plate there, and then now you will see that the area of this plate was given. So we have the area here, which is 2 meters squared, and then the distance was also given. So this is the distance between the capacitor. So the distance between the two metal plates, sorry, it's just 6 millimeters, right? And then we also have the voltage, right? So if we can write all the information given here, we can see that the distance there is 6 millimeters. So if it's 6 millimeters, we're just going to divide this by 1000 because the SI units for the distance has to be in meters. So this is going to give us 0, or we can just write this in this notation. So this is going to be 6 times 10 to the power of -3 meters, right? So now we have the voltage, we have the distance, and between the plate, and we also have the area, right? So which formula here are we going to use? And the area there is in meters squared. This is the correct SI unit, so we can use this formula. The capacitance now is equal to E naught A, just the area there. So this is the formula that we can use there because we have the area and the distance, right? So the dielectric constant there, which is the permittivity constant, is 8,85 times 10 to the power of -12, right? And then 2, which is the area, and then the distance, which is going to be 6 times 10 to the power of -3. So if we check our formula sheet there, the E is a constant there. So now if we do the calculations here, we'll see that the value of this capacitance, the capacitance of this capacitor, it's going to be 2,95 times 10 to the power of -9 farad, right? So now we're done with that question. Now we can move to the next question, 8.2.2. Now calculate the charge on each plate, right? To calculate the charge on each plate, remember we already have the capacitance, right? We know that capacitance, it's going to be 2,95 times 10 to the power of -5. We've already calculated the capacitance, and then we also have the voltage, which is the potential difference there, which is 120 volts. And then now they're asking us to calculate the charge on each plate, right? For us to calculate the charge, we're going to say C is equal to Q over V, right? So we know that the capacitance and charge relate to one another through this formula, which is states that the capacitance now, it is the amount of charge. So this is the amount of charge, right, per volt. Amount of charge that a capacitor can store per volt, right? That is the capacitance. That's the definition for capacitance. So we do have the capacitance here in the situation that is going to be 2,95 times 10 to the power of -5. And then the charge here, it's charge Q, right? We don't know the Q, and the volt, it's going to be 120. Then we can quickly calculate the charge. We'll see that when we do the calculations here for the charge value is going to be, if we can do the calculations quickly there, 2,95 times 10 to the power of -9 times 20 times 120. So this, we can just say this is over 1 cross multiply. When we cross multiply, remember we are going to get Q times 1 is Q, and then that times that is going to give us the answer 3, so that's the answer that we got on the calculator there. It's 3,54 times 10 to the power of -7. 3,54 times 10 to the power of -7 coulombs. That's the amount of the charge on each plate, right? So we're done with question 8. Now we can move on to question 9. And then moving on to question 9 here, we see that in this question 9, we have 9.1. And now the first question, now it's saying that we need to, if we can look at the question there, we need to define the term power in an electric circuit. So power is the rate at which work is done, right? So if you write that, you might be incorrect because they're looking for specifically in an electric circuit. So if they ask you that question there, say define power, mention that this is the rate. So power there is the rate. Is the rate at which electrical energy. Power is the rate at which electrical energy is converted in an electric circuit. So this is just the rate at which electrical energy is converted in an electric circuit. That's the definition for power. Then we can move on to 9.2. They're saying that a heater, so a heater here with a single element is marked 60 watts and 220 volts, right? Calculate the resistance of the heater element, right? So we have that, that according to the information given here, we're given the power there. So that 60 watts there is the power. 60 watt is the power. And then we also have the voltage there, which which is 220 volts. Then they want us to calculate the resistance, right? So for us to be able to calculate resistance here, if you can look at your formula sheet, there is a formula that relates power, voltage, and resistance. And that formula, we write P is equal to V squared over R, right? So this formula can just help us to calculate the resistance, right? So what is power here in this situation? Power is going to be 60, right? And then what is the voltage here? The voltage is 220. 220, it's being squared, and then over the resistance, the R. Then for us to calculate here in this situation, we're going to say this is over 1, cross multiply, and when we cross multiply, we'll get 60R. So we'll get 60R equal to 220 squared, right? And then we can divide both sides by 60. You divide, when what you do on the left, you also do on the right. And then now we can use our calculator there to get the final answer there for the resistance. And the resistance in this situation is going to be, this is 220. You can say this is 220. And then we put square there. We square that. 220 squared over 60. So the final answer there for the resistance, it's 806,75 ohms. So this is the resistance there, and I think you've seen the answer there for the resistance. And then now we're going to the next question. So moving on to the next question there, we can see that we have they're saying that now we have to do 9.3, and 9.3 is saying that the diagram below, so in 9.3 they're saying that the diagram below it shows a circuit that consists of 2 cells connected in series, right? So we do have 2 cells there. Cell number 1, here's the cells, here are the cells, right? Cell number 1 and cell number 2 there, they are connected in series with one another, and then each cell has a potential difference of 1,5. So here we've got 1,5 cell, and then one cell is 1,5, so this is 1,5. And then we also have this one, which is also equivalent to 1,5 volts, right? So all in all, if they are together there, the voltage there, it's supposed to be 1,5 times 2, because there are only 2 cells there, that each of them have got an identical voltage, right? So which I think when you multiply by 2, it's going to be 3, right? So now the question was saying that each cell has the potential difference of that, and then now the 2 resistors with the resistance 3 and that, they are connected there. We can see the resistors here and there, and then now they want us to calculate the voltage, right, across the 5 ohm, or the potential difference across the 5 ohm resistor, right? For us to do this question now, we can ask ourselves, how does the current flow? So the current flows from this positive terminal, and then it goes all the way like this, right? So what is the current that passes through here? We don't know the current that passes through there, but we know that the same current that passes through here, this ammeter, is it's the same current that's going to pass through the 5 ohm resistor, right? So this is how the current flows, and then the current will not divide in this situation because we don't have resistors in parallel, right? Good. So now to answer this question, now we can just first say that we want to calculate V equals to IR for that 5 ohm resistor, right? So now you'll notice that we don't have the current. We don't have the current there, right? And if we knew the current, we're just going to multiply the current with the resistance 5, right? So it means that the big question here is for us to find the current, right? But we know that the current that we're looking for here is the same current as the total current, right? So we're going to make use of the information that we have here. We have the two resistors here. If we can combine them, so if we can combine these two resistors here, we can say R1 plus R2. So combining the two resistors, you're gonna get 3 plus 5 ohm, and the answer here is 8 ohms, right? So this is the total resistance. Then we also have the voltage, right? The total voltage there of the circuit, it's going to be 1,5 times 2, which is 3 volts, right? So because they said two cells that have 1,5 volts, they were the ones connected there. And I think this information can help us to calculate the current. Because V is equal to IR here. And what is the voltage? We have 3. What is the current? The current here we have I. We don't know the current. And then we can multiply with the resistance, which is 8 ohms, right? So we are going to divide both sides by 8. To calculate this, we'll divide both sides by 8, right? And then when we divide both sides by 8, 8 cancels that 8. And then we're left with the I, which is the current. So the current now here is equal to 3 over that, which is 0, we can use the calculator here, and then 3 over 8 0.375 amps. So this is the current that we actually need here to calculate. This is the current that flows here. So now we can use that current, and we say V is equal to IR. Then we'll calculate the voltage that is passing through the 5 ohm resistance. So the resistor, right? So it means that here we're going to say this is 0.375, and then times the resistance. What is the resistance here? The resistance is going to be 5 ohms, and then we multiply the 2, right? So the answer here is going to be 0.375 times 5, and the answer now will be 1,875 volts, right? I hope you're learning. I hope you learned on this question. We managed to calculate the voltage, but the starting point there was to think about what we would have done there. For us to calculate this voltage, we need current, right? For us to calculate this voltage, we need current. And where do we get the current? We're supposed to make use of the information that we had there, because we had the total voltage, and we could get the total resistance. And from the total resistance and the total voltage, we can be able to calculate the total current, which is actually the same current that flows through the 5 ohm resistor, because we don't have resistors in parallel for the resistor, for the resistors to divide the current, right? So this is what we've calculated there, and it's correct, and we can move on to the next question. So moving on to the next question there, we're still doing question 8 there. It's another question for another paper. So now question 8 here. So we have that a 3 volt battery is connected to a circuit as shown in the diagram below, right? So now this is just the 3 volt battery that is being connected to a circuit as shown in the diagram. So we do have here that we have something here that is being connected here that was not discussed, right? But if you follow from question 8.1.1, it's asking us that we have to state whether the capacitor C, so it means that we have this thing here, it's a capacitor, right? So do you think this capacitor here at C, if we have this kind of connection here, do you think it would charge or it would discharge, right? According to the diagram, do you think it would charge or discharge? So the best answer there for this one is that it will actually charge, right? So let's look at the capacitance. Let's look at the capacitor. The capacitor is here, and the capacitor is being connected, and the capacitor is connected to to the cell, right? So the fact that the capacitor is connected to the cell means that it will charge. It will receive those electrons there moving from this side. The current will flow, and those electrons will flow to that capacitor, right? And then as a result, the capacitor will charge, right? So in this situation, you would say it will charge, right? So if they ask if it will charge or discharge. 8.1.2, and then give a reason for your answer. Why do you think the capacitor will charge? So it will charge because it is connected. So it is because the capacitor is connected to a battery. Right, so because it's connected to a battery, or it's connected to a power source, or it's connected to a cell, so it means that the capacitor will charge. Remember, the capacitor is a device that stores energy, that stores the charge, right? So it will store the charge here, and it will charge since it is connected to the battery or the source. This is 8.2 actually. So the next question there, moving on to 8.2, the plate of the parallel plate. So the plates of a parallel plate capacitor are 2.88 meters apart, right? And each plate has an area, right? So remember, we always have to draw something here that shows us the plate of this capacitor that they talk about, especially when it's not drawn, so that we can easily have a picture of what they're talking about. So we always have the area here of the plate, and I think was the area given here. Yes, I think the area was given there, but it was given in 10. It was 10.2 centimeters squared. In this situation, the area is not given in meters squared, so we may need to do necessary conversions that convert it to meters squared, right? So they're saying that each plate, it carries a charge of, so the charge of those plates there is 0.345 NC, nanocoulomb. And then now they wanted us to just calculate, if you can look at the question there, they wanted us to calculate the capacitor, so the capacitance of this capacitor, right? So according to the information that we are given there, do we have the area? Yes, we do have the area. It was 10.2 centimeters squared. So if the area is given in centimeters squared, we will quickly convert it by multiplying by 10 to the power of -4, right? So please recall that when you are given the thing in centimeters, how do we convert centimeters to meters? We divide by what? We divide by 100, right? So dividing by 100, it's similar to just multiplying by 10 to the power of -2. So this kind of conversion, it changes the answer to meters. So the answer here is going to be in meters when we multiply by that. So here, because we have 2 centimeters here, if you look at it, so this is the same thing as times 1 centimeter times 1 centimeter. If you can break it down, then this is similar to saying 10.2 times 10 to the power of -2 times 10 to the power of -2. We do that twice, and if you do that twice, this is as easy as just 10 to the power of -4, which is in meters squared, right? So you can just recall that when the SI units of area are in centimeters squared, you just have to multiply by 10 to the power of -4 for it to be in meters. So please don't forget that. And then now we have the area now in meters squared. That's good. And then now what do we have? We have the distance. The distance was 2.38. It was in millimeters. So please, if the distance is in millimeters, just recall that mm you divide by 1000, right? So dividing by 1000, so when you divide something by 1000, this is similar to just multiplying by 10 to the power of negative 3, because we count the number of zeros here, 1, 2, 3, and then which is negative 3. So this one here, we're going to say 2,88. So just multiply by 10 to the power of negative 3. Now this is in meters. So that this one was in meters squared because we times by 10 to the power of negative 4. And then this one is in meters. Right, so you're going to say, let me write this down nicely. 2,38 times 10 to the power of negative 3. This is in meters now, the distance. And then do we have the charge? Yes, we do have the charge, which is 0,345 nano coulombs. And we know that when the charge is in nano coulombs, we know man P, this is going to be times 10 to the power of, so if it's MC, this one, we multiply by 10 to the power of negative 3 times 10 to the power of negative. So this takes our conversions to coulombs. So you can just recall that if it's nanocoulombs, then it's 9 times 10 to the power of 9. If it's PC, we just times by 10 to the power of negative 12 picocoulombs. And then here we also have this one in nanocoulombs, so it means that we're going to also do another conversion here, so which we're going to just multiply by 10 to the power of negative 9 coulombs. Right, for us to calculate the capacitance, we know the formula C is equal to E naught area over the distance, right? So for us to do the calculation here, we can enjoy the calculation because we've already converted this, right? So we know that this is a dielectric constant at the permittivity value there. It's going to be 8,85 times 10 to the power of, it's on the constant sheets there. You can find it there. And then what is the area in the situation here, the converted area? The area that we've converted here, it is here. We're going to take the area. So we'll say this one is 10,2 times 10 to the power of negative 4 all over, what is the distance? The distance here, here's the distance. It's converted to meters. So we must always make sure that all these SI units, all these quantities are converted to the correct SI units. 2,38 times 10 to the power of negative 3. That's good. And then now we can punch this on the calculator. So without a waste of time there, if you punch this on the calculator there, you'll get that this is 8,85 times 10 to the power of negative 12. And then 10,2 times 10 to the power of negative 4 over 2,38 times 10 to the power of negative 3. So if you punch that to the calculator, we're going to get 3,79. 3,79 times 10 to the power of negative 12 farad. Right, so that is the SI units for capacitance. And now can we quickly do the next question there? We can quickly do the next question. I just want to have some space here. Create some space for the next question there. Is now the next question, it's saying that now we need to calculate the potential difference between the plates. Right, so I'm sure now you've noticed that we're only using this formula C is equal to E naught area over the distance between that, and we're also using this formula C is equals to Q over V. So these are the two possible formulas to calculate capacitance from. and then we use this one when we have the area and the distance when we're looking for the capacitance. Now they're looking for the potential difference. Potential difference is this, right? So this is the potential difference. So for us to calculate for the potential difference, we already have the capacitance, which is 3,79 times 10 to the power of negative from the previous question. We already have the capacitance there, which is negative 12. And what is the charge? The charge, we have it, it's that 0,345 times 10 to the power of negative 9. Remember on the previous question, the 8.2.1, the charge was there, but we didn't use it because we're using this formula, right? So the charge was not used there, but it was going to be useful on this question where they look for the potential difference, right? So for us to calculate the potential difference there, we can make sure that the SI units are correct there before we can substitute. So the capacitance should always be in farad, capital letter F. I've calculated my capacitance there, it's in F, capital letter F. Then now the charge is in coulombs, C. It means that the voltage that we're going to calculate here is going to be in V, right? Potential difference. Now here, to continue with this question, we're going to say over 1, do the cross multiplication here. Then when we do cross multiplication, it means that V, we're going to get 3,79 times 10 to the power of negative 12. V is equal to 0,345 times 10 to the power of negative 9. So the answer here is going to be 3,79 times 10 to the power of negative 12. This cancels that. What you do on the left, you also do on the right. 3,79 times 10 to the power of negative 12. So what is the voltage here? The voltage in this situation, it's going to be the answer on the right, and then we can quickly punch the calculator there and calculate the voltage. Can we do that quickly? Yes, we can do it. 0,345 times 10 to the power of negative 9 over 3,79. Then negative 12. That's good. We got the answer there. Let me check the answer. It's 91,03. 1,03 volts. This is the voltage of that yes, of that question. Yes, we do have the voltage that was applied. So normally the voltage it's the one that gets applied. So this is the voltage applied. Potential difference. So now here we have question 9. Let's do this question quickly. So question 9 here. In question 9, they say that a current of 6 amps is flowing through an electrical appliance with a potential difference of 220. Right, so we do have here that we're given the current and a 9.1.1 that is flowing through an electrical appliance with a potential difference of 220. Right, so they say that 9.1.1, the electrical power can be converted for household and other uses. Right, so name 2 of these conversions or uses of electrical power, right? So we can use this light, you can convert it to light. See that we can convert it to heat, right? We light our homes, we use those bulbs to light up our homes, and then we can also heat. We can use this for heat, right? We can use this for sound, right? And then you can write any of this, right? Any of this too. You can also use it for mechanical energy. So any of these four would do. 9.1.2, calculate the power dissipated, right? Dissipated in the electrical appliance, right? So we do have the current here. The current is 6A, and then we also have the we also have what? We also have the voltage. Voltage is 220 volts. And now they want us to calculate the power. So P is equal to, so there's a power formula that relates these quantities here, P, I, and V. So it's P is equal to I, V. If you check your formula sheet there, you would see it. P is equal to IV, but it's actually written P equal to VI. So if you check there, there's an option, or there's a formula that you can use, that you can relate these quantities. So the quantity V there, it's the potential difference. Don't forget, when you see V, you are looking at potential difference. So don't get confused. It's the voltage. This is 220 times what? 6. Now the answer here is going to be 130 watts, right? So now if the power, they're looking for power in kilowatts, we're going to take that answer, we divide by 1000. So always keep in mind, to move from watts to kilowatts, we divide by 1000. Answer here is going to be 1,320 kilowatts. Can move on to the next question, which is the last question here, 9.2. 2 ohmic resistors. So 2 ohmic resistors, R1 and R2, are connected in series with the cell with negligible internal resistance, right? So here it means that we are going to ignore the internal resistance, right? So we have R1, resistor 1, and resistor 2 here. They are connected. So we need to find the value of R2, right? But what information do we have here? What information do we have here? We have that we have to find the R2. So R2 is unknown, given that the strength flowing through R1 and R2 is 0.5. So the current that is flowing, the current that is flowing there, it's given, and the potential difference across the cell, it's 1.5. So the value for R1 is, so this one, R1, we do have it, it's 2 ohms. But what is the value for this one? We don't know. Right, so we have to be smart here. We have to check the quantities, the information that we have here for us to be able to calculate this resistance, right? So we know that the total current is there. We know the voltage, it's 1.5 volts. It's only one cell, that is 1.5. So this is what we have there. So we don't have to multiply by 2 like the previous question, because this is already one cell and it's given 1.5, right? So this is the voltage, the total voltage. And then what is the total current here in the situation? The total current there is going to be 0.5 amps, right? So I think we can calculate the total resistance from V is equal to IR. So this formula here can calculate the total resistance. So just in case you're wondering where did I get this formula, I think it's there from your formula sheet there. There's R is equal to VI, right? So you can just write that formula there. You will see that the R is equal to V. What is V? The voltage is 1.5 divided by the current, which is 0.5. We are calculating the total resistance here of this cell, and the total resistance will be 3 ohms. Then from this 3 ohms, you will agree with me that the total resistance here, when we add these resistors, R is R1 plus R2. These are the only resistors there. And then now what is the total resistance? It's 3 ohm. And then R1, what is R1? We do have it, it's 2 ohm. Then what is R2? We don't have it, we don't know. Then we can transpose this one and use this equation to solve for R2. So 3 ohm here will be minusing 2 ohm, and which is equal to R2. So it means that the value of R2 here will be 1 ohm. R2 will be 1 ohm, right? So yes, I think if we can do a quick recap here, we're given the total voltage. So we made use of the total voltage and the total current there, because we know that the current flows in this direction, right? And then we know that all these resistors are going to have the same current passing through them, since they are in series with one another. And then now we can make use of this to calculate the total current, so the total resistance. Right. After calculating the total resistance, we go and add the two resistors. Then we can get the resistance. So I hope it's fine. I hope you learned from these questions. But we only covered questions for electric circuits, and also capacitance and capacitor. I hope you learned a lot from these questions, and then I'll be hoping to see you guys in the next videos. And thank you so much for watching this video, and bye bye.